name is Jorge Ramirez. To be talking about the OP-TEE and the power management integration of Trust OS with the current PSCI framework. So the agenda, a little bit explain the reasons for the PSCI interface, define the software stack, detail a little bit the PSCI requirements, and something that is in the specs for the last 2 years, which is when the spec was published. Going to present a system view of the OP-TEE, a developer's view of the PSCI, basically how do we enter suspend states, how do we hot plug CPUs, that sort of thing, and just go through some use cases. So the main issue that the PSCI spec tries to resolve is all the lack of established firmware interfaces that are 32%. At the moment, the main issue that we have is all the platform-specific code that's being maintained in BSP3s, and because it's so specific, it won't be able to be upstream. With ARM64, the intention is to present a clean sheet, so basically a single tree strategy, and for bad or good, delegate all the platform-specific code to firmware. So PSCI defines a generic interface for a series of power management scenarios. Actually, it's very specific in terms of the scenarios that PSCI covers. It's a number of, actually just 4, CPU hot plug, idle management, big little migration, and the scenario. Again, the PSCI is very clear on what it wants to cover. So the secure wall is going to control the power states for the CPU. The normal wall is going to implement the policy and all the performance management. PSCI doesn't contemplate the devices, and things like frequency scaling also are not contemplated by the spec. Feel free to interrupt me at any time. I tend to talk very fast, so if there's anything that's not clear, just speak up. This is a view of the software stack of the 64-bit architecture. Basically, there are a number of exception levels. The rich OS, kernels, and applications go at EL0, rich OS and EL1, a perversion always in EL2, non-secure, and then the secure monitor in EL3, and you have a secure OS and secure apps. PSCI again details the interface between the secure and the normal walls. It uses two conduits, SMC calls, if there is an L3 present. If there is no L3 present, you have to use a type HYD. Later on, well, the communication between the secure platform firmware and the secure OS. So this interface is vendor dependent and is not detailed by the PSCI spec. The way OP-TEE works with the ARM Trusted Firmware, actually what has been done by the security team is they integrated the OP-TEE with the ATF as a runtime service. So basically, when the system boots, OP-TEE registers its hooks with the ATF. So the spec basically is just 5 points. It's going to cover these scenarios, so core idle management, not peripherals. I keep on repeating that, but I think it's something that keeps on being raised. There is a new release of the spec, which I don't know, I think it was released yesterday. I don't know if there is any changes, I haven't been able to see it. But version 02 doesn't include peripherals. The core idle management situations that covers for standby, retention, and power down. From the OS perspective, between the standby and retention, there's no really major differences. Other than external debugger trying to access debug registers on if the core is in rotation state, you won't be able to access the debug registers. Other than that, from the rich OS is the same. Then the power down, you need to manage the context, make sure that everything is safe. Then you have hot plug. So we need a PSCI provides an interface to switch processor on and off.
What difference you make between hot plug and core idle management power down state?
It's the same. Actually, it's the same interface.
Okay.
Exactly the same. Then it discusses, well, it attempts to cover the big little migration in the sense that a trust environment running on the platform, typically OP-TEEs, most of the trusted OSs are not SMP capable. So if you, or if the supervisory software wants to suspend one of the cores or power down one of the cores, it needs to contemplate the migration of the trusted environment to another. It needs to take it out of the way. In that sense, it provides an interface to identify, actually to request the trusted OS to be migrated, and actually first to identify the capabilities present. And sometimes the trusted OS doesn't have that capability, which is the case with OP-TEE. At the moment, OP-TEE cannot be migrated from one core to another. It's to stay. So that's one kernel limitation. Then, of course, since we have power down there, save and restore execution states needs to be present. All the GIC states needs to be saved. So that will be part of the firmware. The untrusted firmware or the platform specific areas of the firmware will take care of the GIC, as well as the two caches and so on. And then also you have an interface for the system shutdown and reset hooks. Since this is very platform specific, each vendor is doing its own thing, so PSCI is going to provide an interface for those. With PSCI 02, some things have changed. So the function identifiers with 01, it were provided with by some firmware tables, the REST-3, CPI. With PSCI 02, the function identifiers have been standardized, so you have a set of functions IDs and all of this. They added a number of functions, activity info, migrate info type, system reset. So all these are new interface, new functions on the interface. And all of them, except those two that I mentioned there, are mandatory. And the other change is some return codes. So if you are moving from PSCI 01 or 202, you need to take that into consideration. So from the OP-TEE system view, I'm sure you've seen this a number of times. Basically, you have a supervisory software, a rich OS, that talks to a secure environment that's running in a chipset that you got trust on enabled using the secure monitor cores. That's the standard interface. Today, since this is talked about OP-TEE, OP-TEE runs in R32, and the Linux driver uses a 32-bit SMC 32 cores. And currently the driver is not upstream. It's in the git tree for the OP-TEE. However, the PSCI Linux driver uses SMC 32 and SMC 64. I'm not sure why. They need to use both of them. Something I need to find out. And this driver is upstream. As I said initially, the OP-TEE is integrated with the ATF as a service. It's a runtime service that can be present or not. If you install OP-TEE with your ATF, you'll have it, and you can run your trusted apps. PSCI will always be there if the ATF supports it. So from the developer's point of view, PSCI reports, obviously, the presence is reported using the firmware tables. In the 318 Linux kernel, you got the device tree representation. You specify the version of the interface that you are supporting, and you got 32 or 64-bit codes. And then the way it communicates is if you got an AF3 present, which is in the case of IETF, it goes over the SMC interface. We'll call the dispatcher. If you register your PSCI service, which OP-TEE does, you have a dispatcher for the OP-TEE for Affinity 0, which represents the core. And the rest of the PSCI service calls for the rest of the platforms, so Affinity 0, 1, 2, are handled in the platform-specific code for your system, for your SoC. So OP-TEE only handles today. I think the situation is changing. I think OP-TEE is going to be able to support calls from different cores. But initially, it's only supporting Affinity 0. As I said, the other affinities are handling the platform-specific code. In terms of how I thought it was relevant when I was looking at the code. This is the way the interface is handled. So the RTF uses a vector table to find out where to call and how to call the OP-TEE. PSCI doesn't define the way the interface is put together, so it doesn't place any restriction on how to call a trusted environment. It just says, every vendor can do whatever they want. This is the way that the OP-TEE was done. So, in these use cases, it was just more, basically just to show the entry points in the code and maybe have a view of the source code involved during the handling of the calls. In the case of a CPU on, use the standard SMP interface. The call gets handled by the SMC. After the SMC, it goes to the affinity level on. At the moment, there's no need. Actually, there's no interface to call the OP-TEE for a CPU on. The platform-specific bits will take any action required for the different affinity levels. Before, the last instruction will be to construct the PMIC to turn the CPU on. And then once you turn the CPU on, it will call into this function, the PCI affinity level on finish, which is the completion of the sequence, and that will set up all the entry points. Continue with the boot process on the second CPU. This is clear. You go from one CPU and boot a different one. For CPU off, basically you can only switch off today with the spec the CPU from the one that you're calling from. You cannot select to switch off any other CPU. I understand that that's a problem for some platforms, and I think that needs some discussion. But the way the spec is defined at the moment, when CPU die is called, basically you're going to power down this CPU. Right? The way to basically to check that the CPU was effectively powered down is to use a second core, simply to check the affinity info of the CPU that we try to switch off. I'm not sure that's ideal. I mean, that's my personal view, but that's the way it's being done at the moment. So basically, the way it's supposed to be working, you do all the platform operations, the Trusted Firmware framework, enter the WFI loop. At some point, the PMIC will switch off the CPU, and then another core will go into the kernel. Another core in the kernel from the SMPC will check that the CPU was switched off.
If I understand correctly, so the Trusted Firmware will configure the PMIC to power down.
Yes.
And the CPU frag handle the voltage scaling of the CPU. That's it.
Sorry?
I mean, on one side, you have PSCI that will power down the power domain and send some command to the PMIC. And for the voltage scaling and the frequency scaling, it's CPU frag driver So both are accessing PMIC, maybe the same kind of register.
Possibly, but I don't know how that resolved. The way I think ARM wants to do it, and maybe someone from ARM wants to comment, is they want to use a second interface, a non-secure interface for that, using a mailbox driver on an MHU. But how any race condition can happen in there, how it's going to be handled, I don't have an answer.
So you also mentioned the ability of the trusted firmware is not always SMP aware.
The OP-TEE is
right.
SMP aware.
So that means
I think that the trusted firmware is not the OP-TEE.
Yeah, I don't know about trusted firmware.
So that's the OP-TEE, the secure OS, and the trusted firmware is the one that goes into the OP-TEE. This is typically SMP, not SMP aware. This is typically is bound to a single core.
And when you want to shut that core off, that's when you have to do that
you need
migration.
to migrate this guy out of the way, if the interface is supported. And today, OP-TEE cannot be moved from what is right.
So this has been a problem on ARM32 firmware for a while, where we have hacky CPU idle implementations that have to do, that basically, like a lot of times the firmware is stuck on CPU 0, so you can't idle the cluster until CPU 0 is done. But if you happen to be, it makes the hardware doesn't have the restriction, but the firmware actually has the restriction.
The firmware, yes.
So but I just wanted to make sure. So if you're not using OP-TEE service or something, and you just have trusted firmware, the trusted firmware stuff itself is SMP aware.
Yes.
Okay.
I mean, that's my understanding. Yes.
Yeah. Trusted firmware runs on every core.
On every core.
Yeah, the SMC will go to trusted firmware on the core you're running on. I was under the impression that OP-TEE was resident on every core, but basically has a lock that prevents it from carrying out actions on more than one core at a time at the moment. Although that's something I think that Jens is in the plans to sort of make it actually SMP capable rather than just have a big lock.
Okay.
But that lock's actually in OP-TEE itself. PSCI provides support for an environment where you've got a trusted OS which is on one core and cannot move. So that's a non-migratable uniprocessor.
Yeah.
And in that case, a CPU off request is allowed to fail on that core.
I see.
If it's migratable, a CPU off request can fail, but there's a migrate function to actually move that to a different uniprocessor core. But that isn't wired up in the Linux drivers at this point. If you're trying to say you're trying to you can't stop idling that core, but you can stop it from being CPU off or plugged off. But we've only just added sort of the wiring up migrate within PSCI because we haven't had anyone from the Trusted OS community saying that they needed it. So at the moment, most of the Trusted OSs have either solved it themselves or are either appear to be MP, even if they only run on one core at any one time.
Which means they're going to have to do something like the CPU idle coupled state, which essentially has to wait for the other cores to idle before they can idle that main core.
A lot of the time,
which is pretty inefficient.
If the Trusted OS is running, then you're actually on secure state, and so the normal world can't ask to idle anyway. Once you're back in the normal world, if the normal world says there's nothing to do, then there probably isn't anything happening on the secure side, because the secure side isn't quite running as an entirely independent OS. If it was, then you might want to come up with a scheme where it would automatically, on idle, the trusted world just migrates its activity to a different core, and it knows which cores are running because it can hook these things. So there's a lot of flexibility, but there probably only are a small number of ways you really want to do this to do it well.
I guess the worry is that in similar to ARM32 case, most people take the simple path first and make these kind of pinned on a CPU or something, and then the firmware gets frozen and signed and flashed and everything, and then you kind of end up getting stuck. And so I just want to make the whole SMP aware thing, make sure we're doing that from the beginning.
So so we've talked to a number of Trusted OS vendors and developers, and we haven't come across any that say no, they need to have, they absolutely need the migrate support, or they are reporting themselves as being single processor. And it might be because they've all basically gone that step of actually at least deploying on all the cores, even if they'd only run on one at a time, because that's where V7 has gone.
Yeah.
So on the V8 Trusted Firmware, we haven't had much pressure or discussion around, no, we absolutely need to have this uniprocessor handling. So it makes life a lot easier for the OS.
Yeah, good.
Excuse me? I have a question. When using PSCI, which means we have to move our platform core from VO1 to VO3. But what if the platform core depends on facility provided by Linux kernel, for example, I2C or anything else? So I saw develop simply duplicate the subsystem from Linux kernel to ATF, which is definitely not a good approach. So what's the best practice? So that's my question.
That's a very good question. I think someone from ARM maybe wants to.
ARM Trusted Firmware is an open source project. If someone wants to develop an I2C framework, it's not on our roadmap, but if there was enough interest, it would be something that we could consider. But we'd also quite happily accept contributions of that nature to put in our driver support, because presumably there will be more than one platform for whom this is interesting. It all depends on how you connect the processor to the power control.
So, have you gone through this already, CPU on and off?
Yep.
So I think CPU on, we've covered this one, haven't we?
Yes.
Yeah. CPU off, I think we've covered this one as well. Suspend, that's interesting. The interface that PSCI presents supports a standby and power down operations, and together with the operations, it creates a couple of fields where you can customize your plan. Basically, those fields are in firmware tables, in the device tree. So if your platform has a number of special configurations that will need to be handled as part of the platform, you will provide those in the device tree, and when the suspend state or the standby state is requested, in the entry, well, not in the entry, in the request field, you will specify which state really you want to go into. At the moment, the kernel today is only supporting the standby interface. That's a simple sort of call. All context is maintained by the processor, and changing from the standby to running doesn't require a reset.
Which kernel is only doing standby? Juno and the FVP platforms have device tree tables which specify power off states instead, or suspend as well.
That's not. I mean, I was checking 3.18. And I don't see anything on the device trees.
Yeah, I can double check with Lorenzo, but no. It's certainly there are device trees, and I'm pretty sure the driver now does. Or upstream driver in the table we've got for Juno specify CPU and clusters as power off states.
The Juno device tree only just went upstream, so it probably wasn't in 3.18.
Right. Yeah. Okay. No, because we've got a copy of that device tree in Trusted Firmware, which we may have those entries in. Okay. Probably have to just double check offline just what combination you need to get the lower power states.
And I'm sure we'll get to.
You're right that for standby, there is no interaction with the dispatcher because the CPU state is totally preserved.
Right.
We just try and get to WFI as fast as possible.
Yeah. But I mean, I was trying to look for those states that you mentioned just to see what happens. And the kernel I was looking into, there were no platform specific states, so there was not a lot that I could see. One interesting thing about the whole discussion is the logic for when to switch on and off, and correct me if I'm wrong, the clusters is left to the firmware. I think that might bring some problems to the supervisory software that's trying to optimize the performance of the platform when under the hood the firmware decides to switch off one of the clusters. I don't know if there is in the next version of the PSCI spec provision for that, basically to ban the firmware from powering clusters if that request doesn't come exactly like that from the kernel. But in principle, the logic, so if you switch a couple of the cores and that's all there is in the cluster, the firmware will shut it down. And I think maybe the kernel wouldn't be happy with that.
Well,
It
the
sounds
kernel
like
specify not to power off the cluster in your request. So you can say suspend to CPU, but not the cluster.
Okay, so you guys specify the affinity. Okay, I think
that's part of the power state parameter.
Okay.
Yeah.
Okay.
Sorry, is this all about system-wide suspend, or it's about suspending something just CPU or cluster?
Single CPU. But the CPU can say, I'll allow you to turn the cluster off as well if there's nothing else running on the cluster.
It's related to CPU idle.
Yes, this is CPU idle.
So pretty much what I could say in the kernel 3 for this. Then the case of the case I was looking at for you, where you can see different clusters that have different power domains and power modes. Using PSCI, all those modes they're controlled by the M3 Cortex. From the software perspective, I think there's a problem here with the arrows. We probably should go to the PSCI. As I was saying from the beginning, the PSCI details as interface between the rich OS and the ATF. Well, in Juno this is called the SCP. That's the one that controls the power modes. Looking into some of the other operations are not detailed in PSCI, and develop a SCP interface using the MHU to control the dynamic aspects of the platform. I suppose all the devices are not covered by PSCI. Because there is an SCPI protocol, and of course the mailbox driver for the MHU. The SCPI protocol, I'm not sure there's any plans for it to be upstream, or if it's going to be extended to support all possible operations in the future. I don't know for that. But one of the things about this interface is it provides two sort of operations, secure and unsecure. So it gives you a lot of flexibility if you want to use that to control some of the dynamic aspects of the power management. And I don't think I have anything else. No, that's it. Any questions or any discussions?
I had a question or comment. So, in CPU Suspend, when you actually dig up the code, it does take it into a low power state. And work out how to get you running with that. Does OP-TEE need to do anything if in a CPU Suspend state where it's going to power the CPU off? I'm asking because switching to PSCI running at EL3 is quite fast, as in the overhead of going in and out of EL3 adds about 1.5 microseconds. Switching from non-secure to secure state to enter EL1 so that OP-TEE can do something, and then back to EL3 in order to then do the power off is going to add probably tens of microseconds to the total time, the total entry-exit latency for a suspend state. But if you're just going to do a CPU power down and power up, this is quite a large proportion then of the actual CPU time spent entering and exit idle, which is not good for idle power management. So the question is although there's a hook there, the dispatcher doesn't have to invoke the OS if there isn't actually something for the OS to do, and that transition to a sort of like powered off suspend state. So although there's the ability to do that hook, the question is does OP-TEE actually require, does it need to do something in a state where the CPU is just going idle into low power states?
I don't know. I don't know if anyone from the OP-TEE team wants to comment. Anyone here? I'll come back to you on that.
So it's more a recommendation that says is just because the hook's there, don't wire it up to the OS if the OS doesn't actually need to do something in that scenario. Clearly, CPU off, CPU on.
Yes.
It's different because OP-TEE might want to keep track of the fact that the OS is no longer running. But idle is just it'll wake up on interrupt anyway.
Should be clearly documented somewhere.
Yeah, I have a question regarding the SCPI, and if anyone's aware of any efforts to standardize that communication.
I'm not sure there are any efforts to that regard. We ask and the current version of the protocol is very much developed for you now. I don't know if the intention is to provide a standard protocol for all those dynamic operations not covered by PSCI using SCPI or whatever other name is given to that protocol.
I'll comment on that briefly. ACPI already has a sort of standard for some of the DVS operations, which is CPBC. So in the interest of supporting that, one of the things we then have been looking at is making that work means actually re-engineering the way we're using the actual hardware MHU channels. But actually that's probably, it's an evolution we actually want to do because we separate out the SCPI sort of message protocol from the underlying transport using the MHU. And we want to do that in a way that allows us to run CPBC for the actual DVFS requests and then some other message protocol for the other things that are done with it, but using the same underlying sort of PCC abstraction and mailbox abstraction in Linux. Because we're wanting to do that and refactor it, that's I think one reason why those drivers may not have been kind of like going upstream, because we don't want to upstream some drivers and then in a few months throw them away and say no, we're doing it differently now. So that's why there's been some hesitation with SCPI. Standardizing everything that you do with the SCP is the question is there sort of like, is that wanted? And at least currently SCPI messages are at least published. Linaro actually, there's a lot in the Linaro document somewhere that that's published with the Juno port. So we're kind of working towards that, but we're trying to sort of get a better abstraction so that it fits in with existing Linux sort of like underlying low-level components. And when we've got that far, then we might look at saying, is there worth value in standardizing further? But it's only really worth standardizing if it's more than just our development platforms that are using it.
I think, yeah, from my perspective, there would be value. Right. I mean, having a generic way of communicating power management for peripherals is very interesting too.
I'll take that feedback back to the guys working on that.
I mean, that's a question that we get asked a lot. You know, with this interface, why it's not upstream, at least the protocol, why it's not. Because we can see there is a PSCI spec, and I think the intention that I heard is that they're going to be developed, OS in development, SCPI sort of protocol spec. I think that's might be on the way.
Yeah, there's not at the level of PSCI, which is really designed trying to be a universal ARM standard, much like the ISA is. SCPI is slightly more, well, it was point solution, and turning that into something then you say is it'll never have quite the status of PSCI, because there are other ways of doing power control. You don't have to have to do it this way. So yeah, I guess the thing is, it's something that over time it might become an emergent thing that becomes something that more people use in de facto standards. So there's not an effort to turn it into a sort of in principle standard. But we'll see.
I have a question for you, since I have me. Is there a consortium to drive the PSCI, or is it just driven by ARM?
No, so it's ARM architecture group that basically does this. If you want to be involved in feedback around this and get involved in future evolution, then Charles Garcia-Toban is just get in contact. So quite a lot of companies have been involved in the review cycle for this publication 1.0. It's not really an issue to have other people involved in that review and have a larger group. But there's not a sort of consortium sort of like running that specification. It's an ARM specification, but we're happy for partners to be involved.
Okay.
Is there such a group for SCPI discussion at all?
But SCPI.
Is there such a discussion?
No, there isn't such a discussion going on. So I'm not quite sure who would. It would probably be Charles again or one of that group. But I'll certainly take some feedback from today about there being an interest in this. If we follow it up, we'll kind of like collect some names of people who want to sort of take the discussion further. But yeah, it's not my space. I won't promise anything other than I'll take the feedback.
Excuse me. Sorry, I would like to talk a little more about my previous question. I2C is just an example. I mean, a power control may rely on more than that multi-thread collaboration or something precise timing control. I mean, is there any way to provide some callback to leverage the facility in EO1 so that we don't have to duplicate our efforts in both EO1 and EO3?
Sorry, could you return back please to the slide where we do CPU on? It's mainly the question related to this. No, CPU on, comma. CPU up.
Off?
Up.
Next one.
Yeah, there. On this slide, for example, I can see a PMIC block. Does it mean that this power management controller is external to SoC? So, just to clarify, so this ARM Trusted Firmware. When we power in on or off some cluster or even some CPU, this could be designed in general in different way. Would it be needed to access external power management SQC through the I2C, for example?
That's just the diagram to me says the PMIC's not in the software. It's outside the CPU.
Yeah. So my question is, if PMIC is outside of the CPU, then Trusted Firmware will need to implement some interfaces to access this.
It depends if it's on the SoC or off the SoC. On the SoC, it's just be memory map.
But I guess the question is, what if it's an I2C, and then you have to reinvent the entire I2C driver that's in the kernel, again in the firmware? Right? So the question, I guess, what he's asking is, can we have a callback from the ARM Trusted Firmware if the call actually happens to be an I2C instead of writing the I2C driver in the Trusted Firmware side to have a callback into the kernel and then come back somehow? Right?
Yeah. And it's not just the callback. You need to deal with potentially contention between the trusted firmware and the rest of the OS if there's anything else on the same bus.
Have you planned some kind of virtualized CPU execution to non-CPU?
I don't know, because the question is coming from up world, yeah, but we switching both CPUs to the low power state, then we can lower the voltage on the wall, this MPU block, just from normal voltage to some voltage which allow us to keep the retention state on internal power saving techniques. And in this case, some communication need to be done with between SoC and external pin. So all this architecture assume such cases, possibility of implementing such use cases.
Yeah, so I mean Juno achieves this because that communication is done by the SCP. So of course that can manage its own I/O framework. There are some in the process of actually doing the power down sequence, there are a number of steps, and at a certain point, returning to run OS code is absolutely impossible because your state of coherency and cache state. And where in that sequence you would actually talk to the power controller to say, right, on the next WFI, when you actually get the signal that the core is in WFI, you're going to remove power. Returning out of the secure world temporarily while you're in a state to be able to run OS code to return to the secure world, apart from the, are we actually going to come back? We don't know, right? You could disappear off, and now PSCI thinks you're in a power off state because we've decided we will go into a power state, but the OS has now decided to do something different. There's a whole bunch of concerns to worry about. I'm thinking that, well, okay, this idea of an OS initiated mode would kind of help you because you're doing a situation where you effectively, the OS knows exactly what state it's going to power down to, so it could actually talk to the power controller and then issue an OS initiated shutdown, and if that actually isn't the state you can achieve, you then have to tell the power controller to revert the previous request. It's going to be very challenging to do it in a way that is both robust
But I suppose that if your PMIC is on the I2C bus, which is shared with other peripherals used by Linux, at this point, there is no trust anymore, because Linux can power down the system anyway without asking the trusted firmware to do it.
Yeah, that's true.
It'd be more logical to have the trusted firmware expose some interface that would allow Linux access to the bus if you wanted to do that. So provide a higher level I2C interface, which the trusted firmware could then audit.
Have you planned to create a virtual I2C controller?
Yeah.
That's so that you can manage all the transactions.
Yeah. So partly in answer to Nico there. So if the Linux could just basically remove power anyway without actually involving the secure side, involving the secure side in the transaction is not one about the sort of like the security of trust zone. If basically power removal could potentially leak your secrets, then you've got a bigger problem than just potentially having the OS kernel being able to power down. The issue is about whether you've actually been able to safely power down that core in a way that leaves the system intact. Because if you just power down the core and you haven't programmed the interconnect and you've taken the core cleanly out of coherency, you're now left with a system that is unstable. So, which is why you want to actually use the secure state and EL3 to actually carry out that stage of the processor exit from coherency. Not because you must do the actual power control invocation from EL3, but it's usually not possible to de-interleave that and do one thing first and then everything else afterwards. Hence the migration of the actual power control interaction to EL3, and sort of trying to find a clean way of separating the two without having to be able to do an undo operation on one way or the other requires some careful thought, I think. But yeah, a suggestion to say, well, maybe the I2C control needs to happen at EL3, then security architects might have issue with that. But pragmatism sometimes is important to consider. Yeah, I think it requires some more thought. There's no neat solution.
So it's a good thing that this issue was raised, I guess.
Yes, it's better to discuss the complicated problems than to hide them.
Yeah, I think part of the problem too is the evaluation for this has been on platforms like Juno, where we're not dealing so much with DVFS or so I think as DVFS that the kernel is going to be controlling. So there's like
well,
what's being
Juno does have DVFS controlled by the kernel.
Yes, but what I mean is that's CPU DVFS, but you're also going to have potentially other for power down retention voltage and stuff. You're going to have. I guess the point is that being raised here is Linux is going to be wanting to talk to the PMIC for various reasons, maybe retention voltage or something, and the firmware is going to also be wanting to do that, and maybe the kernel's doing it for device DVFS, and PSCI is doing it for CPU DVFS, and there's kind of.
No, I just trying to understand. So
yeah.
Previously, what I need to deal with is like PMIC, which is outside of SSC. Okay. So when we like to achieve power retention voltage, we talk to this PMIC, and when like APU is going to the low power state, so both CPU are off, and we'd like to set the retention voltage on APU. Some interaction performed with PMIC. It could be done from Linux side or integrated in SSC or in power management hardware. So actually here, if we are going to power off CPU, then we'd like to power off. Let's say we have 8 clusters, each has 4 CPU cores. Now working only 2 of them. So it's difficult for them to apply a retention voltage on the clusters which are not in use right now. So the question is, it will require integrating PMIC inside SoC distance some level, or still could be outside of SoC. And if it's outside of SoC, then how the trusted firmware should be updated to talk with such PMIC, and which interfaces could be used to talk with this PMIC. So it's not only S2C, it could be anything. It could be something private and secret.
Yeah, the solution is to use a microcontroller, which is what's being done for most of these platforms now.
Yeah, so I mean that's how Juno deals with those potential races between DVFS control and idle. Is that all of those requests are serialized through the SCP control processor, and it resolves. Well, it basically forces an ordering, but can resolve that contention on the system.
Okay. So I think this we can close the session. Thanks.